identifying end behavior of power functions. In figure 2 shows the graphs of f of x is equal to x squared, g of x is equal to x to the fourth, and h of x is equal to x to the sixth power, which are all power functions with even whole number powers. Notice that these graphs have similar shapes, very much like that of the quadratic function in the toolkit. However, as the power increases, the graphs flatten somewhat near the origin and become steeper away from the origin. So you can see here that here's in green is the parabola, which is x squared, and then x to the fourth, you can see that it's starting to flatten a little bit more compared to the quadratic function, and then x to the sixth, you can see it starts to get a little bit more flatter. So again, as it says here, the power increases, the graphs flatten somewhat near the origin and become steeper away from the origin. Now, to describe the behavior as numbers become larger and larger, we use the idea of infinity. And we use the symbol infinity for positive infinity and then negative infinity for the negative infinity. When we say that x approaches infinity, which can be symbolically written as x approaches the arrow with infinity, we are describing a behavior. We are saying that x is increasing without bound. So when you're looking at the x-axis, what it's saying is that it's approaching x-axis towards infinity. Now, with the positive even power function, for the examples, as the input increases or decreases without bond, the output values become very large positive numbers. Equivalently, we could describe this behavior by saying that as x approaches positive or negative infinity, the function f of x values increase without bound. In symbolic form, we could write as x approaches positive or negative infinity, then the function is approaching positive infinity. Now, if we take a look at figure 3, it shows the graphs of f of x is equal to x cubed, g of x is equal to x to the fifth, and h of x is equal to x to the seventh, which are all power functions with odd whole number powers. Now, notice that these graphs look similar to the cubic function in the toolkit. Again, as the power increases, the graph flattens near the origin and becomes steeper away from the origin. Now, these examples illustrate that functions of the form f of x is equal to x to the n power reveal symmetry of one kind or another. First, in figure 2, we saw that we had even functions of the form f of x is equal to x to the n, where n was even, are symmetric about the x-axis. So what that means is if we come up to this figure here, and we draw a line right down to the y-axis, we can fold the page, and then one graph is going to be folded onto the other graph of that. So that's why it's symmetric according to the y-axis. Now, if we take a look at figure 3, we see that the odd functions of the form f of x is equal to x to the n power, when the power n is odd, are symmetric about the origin. So if we look at the origin, and if we drew a line that way, if we folded the page, according to the origin, or if we rotate around the origin, we can see that it would be symmetric about the origin. Now, for these odd power functions, as x approaches negative infinity, meaning if I'm going from 0 to negative infinity, the function f of x, these arrows are going down, which means f of x is decreasing without bond. Now, if we look at the right side of the graph, as x is going to the right, meaning it's approaching positive infinity, then we can see that the function is now increasing without bond. So symbolically, we would write it in this form. As x approaches negative infinity, the function is approaching negative infinity. And on the right side here, as x is approaching positive infinity, the function f of x is approaching positive infinity. Now, the behavior of the graph of a function as the input values get very small, as x approaches negative infinity, and then get very large, x is approaching positive infinity, is referred to as the end behavior of the function. We can use words or symbols to describe the end behavior. In figure 4, it's going to show the end behavior of power functions in the form f of x is equal to k times x to the power of n, where n is a non-negative integer depending on the power and the constant. Okay, so again, as stated here, it says here that where n is a non-negative integer depending on the power and the constant. Now, here we have our graphs. So let's take a look at our scenarios here with our graphs. So here at the very top, we can see that we have a situation where we have an even power and when we have an odd power. And then we have a positive constant, meaning the value of k is greater than 0, and when we have a negative constant where k is less than 0. So we want to make sure that we are paying close attention to that as we look at these graphs. So whenever we have a positive constant where k is greater than 0 and it's an even power, here is our end behavior for this graph. Well, you can see here on the left side that this graph is going up on the left and it's also going up on the right. But the way to look at this is that on the x-axis, as x is approaching negative infinity, as it's going towards negative infinity, and here that's basically saying it in this part here, as x is approaching negative infinity, then the value of the function on the left side is approaching positive infinity. So therefore f of x is approaching positive infinity. Now on the right side of this graph, as x is approaching positive infinity, and as x is approaching positive infinity, well, what is happening to the function itself? Well, this graph is going towards positive infinity on the right side. Okay? Now, again, if we take a look now at the right side, here we have an odd power and a positive constant where k is greater than 0. So, as x is approaching negative infinity on the left side of the graph here, and again, as x is approaching negative infinity, then we can say that f of x is approaching negative infinity, which means that this graph is approaching negative infinity on the left side. Now, as x is approaching positive infinity, meaning it's approaching positive infinity, well then the function is also approaching positive infinity. Okay? So you can see the end behavior, and it's all based on what the graph is doing. Let's take a look at the next scenario here where we have an even function again. So we still have an even power function, and now it's a negative constant. So what's happening is this graph is now flipped according to the negative value. So we should see that as x is approaching negative infinity, which is written in that form, then what is the function doing? Well, the function is approaching negative infinity. Okay? And then on the right side, we can see that as the function is approaching positive infinity, and as x is approaching positive infinity, then we can see that the function of the graph is approaching negative infinity. And let's take a look at the last graph here. So the last graph tells us that we have an odd power where the value of k is negative. So here, as x is approaching negative infinity, then what is the function doing? Well, the function is approaching positive infinity. And as x is approaching positive infinity, we can see that the function is approaching negative infinity. So it's really important to understand, what's happening with the graph and another way of saying this is, instead of saying as x approaches in negative infinity and then f of x approaches negative, you can say that the input approaches negative infinity as the output is approaching negative infinity, and so on. But again, it's really important to understand the end behavior of the graphs as we move forward into this section.